I'm going to be talking today about creating iRISE-SOLES, curating evidence for interventions to improve reproducibility. So iRISE is a large EU project that I'm currently working on with the overall goal to improving reproducibility in science. There are over 35 members across 15 partners from various organisations and universities and across 9 countries. We're taking an integrated approach to understanding, investigating, and guiding strategies to address irreproducibility. So we know there's lots of potential solutions or interventions which target various people, researchers, journals, institutions to improve reproducibility, but we don't really know what works and in what context. So what we're trying to do is build an evidence base to understand what works and what doesn't. So there's 7 work packages in this project, and I'm part of work package 2, where we're looking to systematically identify and evaluate candidate interventions to improve reproducibility. And our first objective, and my personal main objective, is creating iRISE-SOLES, is generating a complete overview of the existing interventions. So SOLES are systematic online living evidence summaries. They're effectively living databases which provide a comprehensive overview of all of the existing evidence in a given research field. We're looking to create a living community hub for primary researchers and systematic review projects, with the goal of identifying potential gaps in the literature. There's a little snippet of the SOLES paper written by Dr. Caitlin Hare, who I've been working with very closely on this project. We'll give you a link to that at the end. So I'm going to quickly run through the workflow for setting up a classic SOLES project, and I'll go through these steps in a bit more detail, focusing on how we have done it for the iRISE project. So it starts with a broad systematic search across multiple databases to capture as much literature as possible. We then deduplicate these citations. We then use machine-assisted screening to help us screen the papers for relevance. There's often thousands, sometimes hundreds of thousands of papers that need to be screened. So we use a machine learning algorithm for that. We then use various automated methods to annotate this data for various things such as intervention, outcome, risk of bias, and as well as transparency metrics such as open access status. So these each SOLES project has their own SQL database, and each SOLES project then has their own web dashboard. We currently have around 10 SOLES projects running or being set up. These are in various fields such as stroke, Alzheimer's, psychosis, depression, and more. So step 1 is the identification stage. So here's part of the broad systematic search for iRISE. You can hopefully see a lot of terms in there that you would associate with reproducible science. We created this search string by using a gold set of papers compiled by some of the reproducibility experts within the iRISE project. We then made sure all of these papers and more were captured using these search strings. So across the databases with this large search, we gathered just over 123,000 papers. We removed about 55,000 duplicates, which left us with 68,995 unique articles. So step 2 is the screening stage. So from those just under 70,000 articles, we randomly select 5,000 to be manually screened. So these are dual screened with a third reviewer reconciling the disagreements. So there were over 10,000 screen decisions made in total, which is quite a massive task. We were fortunate enough to be able to use some screen decisions from a couple of ongoing reproducibility projects we've been collaborating with called Osiris and Tier 2. So we then use these decisions to train a machine learning algorithm. So the way that works is it gives each paper a score between 0 and 1, a probability score between 0 and 1, 0 being irrelevant and 1 being relevant. We then take a threshold. We take a threshold which has captured 95% of the relevant papers in the test set. This maybe sounds like I'm going quite deep, but yeah, once we've captured 95% of the relevant papers within our test set, that's where we take the threshold. So ideally in the final set, we have 95% of the relevant papers. It will introduce a little bit of noise in there as well, but we feel like it works quite well. So that left us with 16,832 relevant studies to be annotated. So this is a stage I'm mostly going to be talking about today. Once we have the studies, what data are we looking to extract and how do we annotate almost 17,000 papers? So we're looking to extract the interventions evaluated, who provided the intervention, who the intervention was aimed at, the discipline, research stage, the location, the outcomes, and the evidence type. By evidence type, we mean we're looking to distinguish between these two types. We've got controlled studies, studies which directly evaluate an intervention to improve reproducibility using experimental approaches, such as randomized controls trials or controlled observational studies. Or we've got uncontrolled studies, which is everything else that doesn't fit within that first category. So other types of research, cross-sectional studies and theoretical frameworks. So in a classic SOLES project, this is how we would annotate these tens of thousands of papers. We use a regex-based approach. Regex, or regular expressions, are patterns designed to search for and match specific words or sequences within text strings. So I've tried to give you a little example of how this works if you've not seen this before. Here we've got a drug called alteplase, which I believe is a common stroke drug. And underneath that, we've got all of the alternative ways or phrases or any other way that you can say that that drug. We then run this code through full text or abstracts, and it tags every time that this name or any of the alternative names are discovered. And we do this so we have a regex dictionary that contains over 17,000 different terms, mostly drugs and interventions, but we've also got models, outcomes, species, countries. So this is how we would usually annotate studies within SOLES, but we had to do things differently for the iRISE project because we don't have these regular expressions for these reproducibility terms, and it's a lot of work. It's a lot of work to try and create these and set these up. And for these terms, we weren't sure. There's so many different ways to say these things. We weren't sure if it would work at all. So I've given a little example of that at the bottom of what an iRISE intervention might look like. And yeah, as you can see, there's many different ways to say that. So we look to explore other methods, which is where large language models came into it. So I'm not going to talk too much about what a large language model is. I'm sure everyone has used ChatGPT and has seen the new, or I don't know if it's new, the Google AI response. But large language models, they are artificial intelligence systems trained on vast quantities of data to understand and generate human-like response. They can be used for things such as text generation, classification, which is what we've been doing, summarization, really good for coding, language translation, and sentiment analysis. I guess a basic example of sentiment analysis, if you're not sure what that is, it would be if you had maybe like an Amazon review that didn't have a star rating. You can use large language models to decipher whether that review is positive or negative or neutral. And yeah, there's many variations of that, but that's kind of how it works. So for this project, there are many different types of large language models out there. For this project, I tried quite a few different models, focusing on these three, on the OpenAI GPT models, Llama 3 and Mistral. I started off using the OpenAI models mostly because they were kind of the easiest to use and had the most documentation. It was easier to like get started and get results and see how things were going. But then I did branch out eventually. So there's many different methods you can use when working with large language models as well. So you've got querying, you've got your basic question and answering. You've got fine tuning, which is fine tuning is when you take a pre-trained model and give it more data to train it further for your specific purpose. So it gives you a custom model to work with. I did try this for this project, but to be honest, I never had enough data to work with. It would have required hundreds and hundreds of papers that are annotated by humans, and I didn't have that. Zero-shot learning is maybe when you would try a classification task, but not provide it with any training material from your side at all. You would just be like, classify this, and see how it performs without anything. Few-shot learning is something that we did quite a lot, which, similar to fine-tuning, you would provide examples of what you're doing within the prompt. So within the prompt itself, I would say, here's an abstract, and here are the human annotations, or abstract or methods, and here are the human annotations for this text. And I would give it a few examples of that, and then I would say, and now do it yourself. Embeddings are quite a complex vectorization process, which I don't really know enough about, and didn't explore too much. But I would like to. We also tried out different data for this. So we were working with title and abstract, or title, abstract, and methods, or just the methods. So we were trying different chunks of the text to see how it performed. We didn't really use the full text too much. I think the main problem with this was that there are token limits and occasional costs when using the large language models, and obviously it can get computationally very heavy if we were to put in 17,000 PDFs for annotation. So here's an example of an early prompt. So this was using GPT's 3.5 Turbo. So at the start, you kind of tell the model what kind of model you want it to be. You're hopefully a helpful research assistant. Feed it some text and ask it to classify this as one or more of these disciplines and no other discipline. If you're unsure, choose other. If there's more than one, separate by this, and don't provide any extra text. So yeah, you've got to be quite blunt with it, and to stop it spouting nonsense, really, which I discovered. So this isn't obviously this won't be one of my very first prompts. By this stage, we've realized that it performs better if we feed it a category list and ask it to be like, decipher between these in the list, and don't choose anything else. So moving on, this is more like what the final prompt looked like. So we're asking to extract data in the text provided into a certain shape which was needed for evaluation. If the data is not present, return unspecified for that field. So yeah, here are all of the categories. We're saying what intervention has been evaluated in this study. So this is just part of the prompt. The prompt was really long, and for each category we had quite a few like stipulations that we had to put in there. So we would say select the fewest number of options possible. Going back, just going back quickly. So the discipline list that you see there, we had that for each one of the categories. So as the human annotations were happening at the same time as this process, I was getting a list of interventions and a list of intervention providers that was getting longer and longer. So I was kind of restricting the answers of the large language model, and that definitely made it perform better. And here is just an example of the kind of outputs we were looking at. So evaluating the performance was quite tricky. Obviously, it's quite easy when something is just 100% correct or 100% incorrect. But what we came across quite a lot, if you can imagine, there are multiple interventions tested in a paper, and you're asking the model to pick up all of them, compared with multiple human annotations. So if you look at the second bottom line in that table, you can see the model has correctly predicted data sharing policy / guideline, and then it has predicted other reporting guidelines, checklists, or standards, whereas the human says Prisma guidelines. So these were quite difficult because, well, this example is not really wrong. It's predicted that there are other reporting guidelines, but it's not being able to name them. So we had to work out a way to kind of to evaluate these ones which weren't 100% correct, but definitely weren't wrong. And then underneath that, you've got another example where the model has predicted 2 of the 3 interventions, which were annotated by the human. And this also worked the other way around, where sometimes maybe for example, the model would predict 3 annotation. The model would predict 3 interventions, but the human has only annotated for 2. And this occasionally happened where we would go back and look at the paper, and actually the model was right. And I'm not wanting to. I may sound quite like I'm an advocate for AI here, but I'm just wanting to present kind of what we did, the method that we went for here. I'm certainly not promoting massive use of AI and that it should completely take over. So here are some of the initial results. You can see it performed quite well on things like the target population and the discipline down the bottom. And for some reason, it struggled with the intervention provider. Now, because this project, we're looking at interventions to improve reproducibility in science, I felt like the intervention performance wasn't quite where we'd like it to be. So we looked to see what we could do to improve this performance. So we went back to the evidence type, and we discovered that the model was performing better when it was annotating controlled studies as opposed to uncontrolled studies. So we decided that we were going to split the data into 2. So we ran the model just to decipher between these 2 study types. Yeah, and the reasons for this were the performance, the cost as well. So again, as I mentioned earlier, if you're running masses of text through these models, some of the models charge you per token, and a token can be thought of very similar to per word. And so the costs were going to escalate quite a lot. And looking at control studies was in line with our initial proposal. That's what we had set out to do, was to gather the evidence on these control studies. So when we ran this, yeah, we got this performed quite well. This had an accuracy of about 82%. I know accuracy isn't sometimes the best method to evaluate these, and I'll speak about this a bit more in a second, but that left us with 2,441 type 1 studies to take forward for full annotation. So these were the improved results once we ran it again, but only on the controlled studies. So we discovered for this, after trying, for each one of these stages, we're trying all the different models, but we're trying many different models and different methods. So we discovered for this, GPT's 4.0 at the time was the best model for this, which was the newest OpenAI model. And it was new at the time, it was very new. And the best method for this was the few-shot learning, where we fed it a few examples within the prompt itself, using the title abstract and the methods. So this is just a bit of an overview of how that process went. So we had 138 studies were annotated by humans, 40 of which were excluded. So we didn't use them for any training or testing. So we took the other 98 forward, 10 of which I was using for a very long time on the initial prompts until, because as I say, these things were all kind of happening at once. So that gave us 35 test articles, and then we kept 50 unseen annotated papers aside for validation at the end. And yeah, so that left us with 2,441 priority articles that were fully annotated. There are 16,832 in relevant papers in the database, and then we use other methods that we use across our SOLES projects, like OpenAlex and a tool called OddPub for extracting transparency metrics. So we fully annotate. We fully annotate as many papers as we can with these other metrics. And we feed all of this into our web dashboard, which I'll give you the link for in just a second. This went through a couple of phases. We finished one around Christmas that we had a stakeholder forum that had researchers and publishers and funders look at it and provide feedback, which we then took into account to produce this kind of final model. So here's one of the pages. This is the evidence map that was created just for this project, but we will be looking to roll this out over other SOLES projects. It's a little bit small, but if you can see, I've selected computational reproducibility as an outcome measure to look at up in the top left, and just on the y-axis there, you've got the interventions to improve computational reproducibility across different disciplines. And then, so in the one that I've selected there, you can see there are 30 data sharing, 30 papers looking at data sharing policy/guideline to improve computational reproducibility. And this is another page looking at the location of the data. So I've highlighted the University of Amsterdam there. And again, I've selected computational reproducibility as an outcome. So you can see the filtered number of publications. So there are 5 papers from the University of Amsterdam targeting computational reproducibility out of a total of 47 papers we have in the database from Amsterdam. So the irony is not lost on me at all that I'm working on a large reproducibility project using a method which is known for being almost impossible to reproduce, and now presenting this to the reproducibility group. So these are some steps that we took to try and make this more reproducible. So there are a number of arguments within the function. You can set the seed, which controls the randomness. The temperature controls the creativity. So we wanted it to be not creative at all. We wanted it to just give us what it thought what I thought the answer was, and do not be too creative. And similar with the presence penalty, the version's can sound like quite an obvious one, but I guess there's new models being made all the time and updates and stuff. So I guess making sure you're using the same model and version of that model is quite important. Restricting our category choice. I guess this was one of the most important ones when we started to see results. And so as I say, when we fed in the intervention, the provider, we provided it with this list, and we said, choose primarily from this list, and if it's not on the list, then only choose one or two other options. We weren't giving it free rein to just generate whatever text it wanted, and we really did try and restrict that response. And I guess, so evaluating performance, at some point we would like to write all this up, and we would like to get a paper out of this and write it all up. And I think one of the most important things we can do is, I guess, transparency about what we've done, and that at each stage we ran the model multiple times on the exact same prompt. And I think how you evaluate that and say this, we're not saying that if you run this once you will get these results. We're saying maybe if you run this 5-10 times, your performance should fall within this range of results. And yeah, I guess this links into the idea that SOLES is aimed to provide an overview. Going back to the start, we're looking to provide an overview. We're not saying that every paper in here has been annotated 100% perfectly, but hopefully once you gather all the data together and you step back a bit, you can it does provide a comprehensive overview, and you can see trends and what's happening within the data. So next steps. So this is the first version of iRISE-SOLES, as we're kind of calling it. This was only just finished about 6 weeks or 2 months ago, and we're constantly looking to make improvements to the app and add pages. So yeah, feel free to make suggestions or send us some ideas. The database and the app aren't currently living like the other SOLES projects. We're still trying to work out how regularly we should update the database and run the large language model scripts. Most of our SOLES projects are fully automated and update every week. As this database is a lot smaller and than say like our stroke database, we may only have to update this one monthly, but we're planning on doing this by the end of the month. Yeah, I'd like to improve the performance. There's new models coming out all the time. If we had a few more annotated studies by humans, we could explore more methods, I think. We didn't spend nearly as much time splitting the evidence type between the controlled studies and the uncontrolled studies as we did on the full annotation. I think if you can remember, the accuracy was around 82%, which, as I said, isn't a great metric for evaluating performance. I think we could start look further into like the sensitivity or the recall and try and make that as inclusive as possible, which would introduce a little bit more noise, and there would be more than those 2,441 studies, but it would be good to know that we're definitely gathering as many of the relevant ones as possible. And yeah, extending SOLES out of the systematic review space. So we develop SOLES with systematic reviews in mind, but we know that they're of interest to lots of people and different types of users, such as publishers and funders. And we would like to get as much feedback as we can from different users to eventually broaden the scope of SOLES. Yeah, thanks very much for listening. If anyone's got any questions, I'm happy to have them.